So this is acid catalyzed hydration. So we're going to add a proton to one carbon, and we're going to add a hydroxy to the other carbon. We have to figure out where these carbons, where the hydroxy is going to go and where the hydrogen is going to go. So this is going to be our Markovnikov's addition. We're going to have, we're going to end up with putting the hydroxy on the more substituted position. So this is the more substituted position, so that's where the hydroxy ends up, and the hydrogen ends up on the more substituted position with the other hydrogens. Okay, so let's look at the mechanism. We're going to have a pi bond here, and these electrons are going to snatch this proton, and the electrons attaching it to the oxygen are going to go back on the oxygen. Okay, so the hydrogen can go here or here. If it goes in the second position, this one, then we'll make a tertiary carbocation, and that's going to be more favorable. So the hydrogen goes on this position, and we've made a tertiary carbocation. Now that carbocation is going to be attractive to our water molecule. Oxygen here has a bunch of electrons, so it can be a nucleophile. It's going to, so this water is going to attack the carbocation, and we're going to end up with a water just attached. And it's got a positive charge. Then another water molecule is going to come along, and it's going to attack this proton, and the electrons joining the proton to the oxygen are going to go back to it, and we'll end up with this. Okay. It's very tempting here because we end up with a hydroxy to say that we're going to add a hydroxy at this step. But remember, this is called acid catalyzed hydration. We don't have any hydroxy. There is no hydroxy in the solution. We do have water in the solution, but we don't have any hydroxy, so you can't add hydroxy. Now we want to control the position of the equilibrium here. We've got, we can have addition, and that makes, we've already talked about, this form here, or we can have elimination. Okay. Using straight Le Chartet's principle, if we have more water, the forward reaction will be favored. So more water favors addition. So we find addition with dilute acids. So if you remember your Le Chartet's, if you add more of a reagent, you favor the forward reaction. If we remove a reagent, then we'll favor elimination. So elimination is done with concentrated acids. Removing water will shift the equation toward the reactants. So let's look at the stereochemistry of our acid catalyzed hydration. Go all the way down here. The intermediate carbocation can be attacked from either side, so that results in both a racemic mixture if a chiral center is made. So we end up being racemic if you make a chiral center. So you said pay attention as you make these molecules if you've made a chiral center. Okay, so let's draw the mechanism for this, so just so we get some practice of the mechanism. This would be a good place for you to stop the tape and do the mechanism yourself, and then you can watch me do it. So we've got some pi electrons here, and they go out one day and steal themselves a proton. These electrons then go to live on the oxygen. The hydrogen that they've added adds at the least substituted position and makes a tertiary carbocation. This carbocation is interesting to this water molecule, and I'm going to change colors again. The electrons here on this oxygen are attracted to the positivity there, and we get a water molecule stuck on the side, and it's got a positive charge on the oxygen. So another water molecule comes along. We'll do it in red again. And it's going to steal the proton, and these electrons will go back and live on that oxygen, and we end up with a hydroxy. The second example, the pi electrons here steal a proton, and then that hydrogen that's right there ends up at the least substituted position, giving us a tertiary carbocation. That's supposed to be a plus sign there. That's attractive to a water molecule, and it comes in and attacks that carbon right there, and we end up with a water stuck on the side. Then another water comes in, and it's going to remove this proton, and we end up with the hydroxy.